Students, so today let us discuss about the lattice specific heat. So specific heat, it is the energy that must be applied to a mole of solid to raise its temperature by 1 degree. So what happens when heat energy is applied to a solid is that the temperature of the body rises and its internal energy is increased. Then what happens when internal energy is increased? When internal energy is increased, there will be an increase in the vibration of atoms about their main position, and there will be an increase in the kinetic energy of these free electrons, and correspondingly this there will be lattice vibrations in the solids, and this lattice vibration will contribute to the specific heat, and they are known as the lattice specific heat or lattice heat capacity. Then an increase in the vibration of atoms about their main position that corresponds to the lattice specific heat, and an increase in the kinetic energy of free electrons causes electronic specific heat, and usually it is measured in at a constant volume, so we call it as specific heat at a constant volume, and the expression for it is du by dt under constant volume. Now we have different theories to define the lattice specific heat of solids at by the with the temperature. The first theory is the theory introduced by Dulong and Petit, and which is known as the classical model, and which is based on the kinetic theory of gases. So according to this theory, according to the kinetic theory of gases for monatomic gases, at a temperature T, the kinetic energy is given by 3 by 2 kT, where K is the Boltzmann constant and its value is 1.38 into 10 raised to minus 23 joule per Kelvin. Then and with an energy half kT associated with each degree of freedom. So each atom is associated with 3 degrees of freedom. So for each degree of freedom, an energy associated is half kT by the kinetic theory of gases. Then we have for the translational degree of freedom, we have 2 additional degrees of freedom, one so corresponding to each translational degrees of freedom. That is, the energy associated can be kinetic energy or potential energy. So if there are n atoms in a solid, in a mole of a solid, the total internal energy of the solid is given by, so it is 3 into 2 into n into half kT, that is equal to 3 nkt. Nk is n is the Avogadro number. If n is number of atoms multiplied by the Boltzmann's constant, for 1 mole it will be 3 RT. 3 nkt is equal to 3 RT. For if n is equal to Avogadro number, it will, for 1 mole of substance, total energy will be equal to 3 RT. So the conclusion is that that is, each atom is associated with the 2 translational degrees of freedom, and associated with which we have one kinetic energy and potential energy, and for each atom we have 3 degrees of freedom. So corresponding to each degrees of freedom, we have energy associated is half kT. So for n molecules, the energy associated will be it is half kT into then for 3 degrees of freedom, 3 degrees of freedom it has. So into 3 into corresponding to each degrees of freedom, one translation symmetry. So you have to multiply it with again 2 into n number of atoms. So the expression for total energy according to the kinetic theory of gases, it is 3 RT. Then if we calculate the specific heat, then it is equal to dE by dt, and dE by dt, it is a constant, d by dt of 3 RT, that is equal to 3 R, and the value of 3 R is equal to 5.96 calorie per mole per Kelvin, and the unit here is calorie used we have. So it is 5.96 calorie per mole per Kelvin, and which says that the specific heat of the solid is for all solid it is a constant. But if we examine the real case, we can see that you can see a graph here. The variation of the temperature. This is a graph showing the variation of temperature. Temperature is taken along the x-axis and CV is taken along the y-axis, and the shape of the graph is like this. This is the shape of the graph. You can see here. This is the actual graph, but according to Dulong-Petit law, it is a constant. It's a constant. It is equal to 3R. So something wrong with the classical model for specific heat, and we have to correct it by using modern theory. So, and this is true, the Dulong-Petit law is true for substance which is atomic weight is less than 40, and temperature is almost room temperature for some of the elements. In all other cases, the variations of this or at it is correct at room temperature, but when temperature is below that value, we cannot apply the Dulong-Petit's law, and we have to modify the results by using the modified laws of this material science. So, at low temperatures, the specific heat of all elemental solids is found to approach zero, actually, as T cube in insulators, and it is variation is T. The variation is proportional to T in metals, and in superconductors also the drop is very fast. And in certain magnetic solids, there is a large contribution to the specific heat near the temperature at which the magnetic moments become ordered. And another property we can see is that the number of low atomic number and high melting point elements such as carbon, silicon, etc. show lower specific heats than predicted by Dulong-Petit's law, and a large number of electropositive metals show an increase of specific heat above the maximum value 3R with an increase of temperature. So there are a lot of variations from the Dulong-Petit's law is obtained for several metals. So we have to explain, or we have to modify the theory of specific heat using some other conclusions or some other theories in the expression for specific heat. Usually in the classical model we have treated the atoms as harmonic oscillators. In the harmonic oscillator, energy distribution follow the Maxwell-Boltzmann distribution, which we have studied in our statistical classes. And the average energy in statistical distribution, Maxwell-Boltzmann distribution, is given by the expression E bar is equal to integral E epsilon or E exponential minus E by kBt dE divided by integral exponential minus E by kBt into dE, and by substituting for E in the classical model we have E is equal to P square by 2m plus half m omega square x square. So you can substitute that and find the expression for average energy, and it is found to be kBt, and that can be you can watch a video by Ray Studies lecture number 27 about the solid state physics, where you can see the detailed derivation of this expression, and the value of this specific heat is obtained to be the value of the average energy is obtained to be kBt. You can see from there, where we need not much like that. For if you are interested, you can watch that video to obtain the derivation of that, to get the expression of kBt. So our conclusion is that according to Dulong-Petit's law, the CV is almost a constant, but in actual case there is a variation of CV with respect to temperature. In order to resolve that the disadvantage raised by the Dulong-Petit's law, Einstein introduced a new model for the specific heat, and by using the Planck's quantum theory, we have considered the quantization of energy. And in crystalline solid made up of n atoms per mole can be regarded as an array of atoms of oscillators vibrating in three independent directions with a constant frequency nu, and allowed energy states are integral multiples of h nu, and or it is also mechanically equivalent to a 3n independent oscillators. So in the classical 3 we have treated the harmonic oscillators as having continuous energy, but here we are treating the harmonic oscillators as having energy in some integral multiples of energy. You can take it the total energy of the system. The energy is taken as h cross omega you can take, or in some case we can take it as n plus half h cross omega. En is equal to n h cross omega, or you can take n plus half h cross omega. Also take we can take where this half h cross omega stands for the 0 point energy. So CV for this half h cross omega is independent of t, so it does not contribute to CV. So we are can neglect that term for the study of CV. So we can take the value of energy as nh cross omega where n equal to 0, 1, 2, etc. Now according to the Boltzmann's distribution, the number of oscillators Nn of each energy state is given by Nn is equal to n0 exponential minus En by kt, which is equal to n0 exponential minus nh nu by kt, where n0 is the number of oscillators in the zero energy states. So it is temperature dependent. Number of oscillators having energy, number of oscillators Nn of each energy state, it depends upon the temperature. Now in this case also we can find out the average energy. Average energy you can find out using the equation. Average energy is equal to summation n equal to 0 to infinity, as we have already discussed, the exponential En exponential En exponential minus En divided by kBT whole divided by summation n equal to 0 to infinity exponential, then the same term exponential minus En divided by kBT. So this is the general expression for average energy in the case of harmonic oscillators which obey this Maxwell's Boltzmann distribution, and the value of which is found to be h nu divided by exponential h nu by kBT minus 1. So this is the expression for energy, average energy. Here also that lecture number 28 of the same lecture series, you can find the derivation of these. We need only this type of expressions because we are concentrating on certain other factors here, not on the derivation. So the total energy you can find to be, we have for each n molecules we have, and for each one we have 3 degrees of freedom. So it is total energy is equal to 3 nh nu divided by exponential h nu by kt minus 1 by considering the Planck's quantum theory. So from this the expression for this specific heat CV is equal to dE by dt, where you can differentiate this. On differentiating this we will get 3 nh nu is a constant, then 1 by, you can treat this as 1 by x. So 1 by x means the differential of which is equal to minus 1 by x square. So that is minus 1 by exponential h nu by kt minus 1 the whole square into, then you have to differentiate this expression with respect to t. So the differential exponential is again exponential h nu by kt. Then the factor along with the t is h nu by k is a constant. Then in the differential of 1 by t is minus 1 by t square.